gonna do is chapter 1, critical thinking skills. Critical thinking skills is important for mathematics, right? And the first thing we're gonna do is inductive and deductive reasoning. Are these words familiar to you? Inductive and deductive reasoning. They're so confusing, right? When I was little, I was always confused about inductive and deductive. Who's which? That is confusing. But I want you to know the difference between inductive and deductive reasoning. Can anybody explain what's the inductive reasoning or deductive reasoning? Okay, let's think about your geometry class. I know some of you love the geometry, right? How many of you like geometry? Proving. Yeah, thank you. I love geometry too. Geometry is one of my favorite courses. Okay, so in geometry, you were given a lot of theorems, right? And you proved it. What kind of reasoning was that? Do you think it was inductive or deductive? Okay, how many of you think it's inductive? How many of you think it's deductive? Okay, it's deductive. So deductive is you already have the theorem or generalized the term there and you're proving because it works for everything. But inductive reasoning is you are looking at specific cases, okay? And you're gonna look at all the specific cases by observation or by looking at the pattern and say, maybe then the result should be this, the pattern should be this, okay? You are generalizing from the specific. You see the difference? So if you start from the generalized one and go specific case because of all triangles, with the sum of the angles of a triangle is 180. If one angle is 60 and the other angle is 60, the third one should be 60. Then it is deductive reasoning. But by looking at all the triangles that you are given, saying that, oh, this is 60, 60, 60, this is 90, 45, 45, and this triangle has 20, 80, and 80. Oh, all triangles have sum of 180 angle. Then it becomes inductive reasoning. Okay? So, if we are doing the science, for example, you are doing some experiments, and you can put some hypothesis there, right? Writing the hypothesis, do you think that's inductive or deductive? Is that firm conclusion? Or you're just guessing and assume that this is true and you are doing some experiment, right? So it's gonna be inductive reasoning. Okay, so we use the inductive reasoning in scientific method a lot of times. So inductive reasoning is the process of reasoning to a general conclusion through observation of specific cases. Okay. Again, all of these notes are on resources on the CSSC online. Okay, so you don't have too much time writing this down and copying it down. So we use inductive reasoning for scientific method, and we already know the hypothesis or conjecture. That's just assumption based on your observation. Okay, you don't have to write all this. Okay, so I'm gonna just move on. Okay, so let's look at this example. If two odd numbers are multiplied together, will the product always be an odd number? Let's use our inductive reasoning. So pick some numbers, okay? Pick some odd numbers. Pick two odd numbers. Give me two odd numbers. 7 and 5. 7 and 5. 7 times, both are odd numbers. 7 times 5, 35. It is an odd number. So okay, is that enough to prove that all two odd numbers multiplied together, the product is odd number? No, it's not. We just had one case there, right? So give me more. 9. 9 times 3. 3. What is it? 27. Oh, it's an odd number too. But we have only two cases, so we need more. Give me more. 11 times 3. 3, thank you. So 33 is also a number. So far, all our numbers that we picked as 2 are numbers, the product is odd number. Can we still conclude the all odd number times odd number is always odd number? No, we can't. But we can assume, we can put the hypothesis, right? So it's called what reasoning? Inductive reasoning. Okay, let's try this. Pick any number. So we have 30 students here, right? Everybody can have different number. Keep that in your mind. Did you pick your number? You got that? Multiply that number by 4. I have mine too. Okay. And add 2 to the product. You got that? If you need to write that down, you can do it. Divide the sum you have by 2. And subtract 1 from that quotient. You have it? So how about you write down your original number and the result number? Can you write both down side by side? And pick another number, different number. I'm gonna do this procedure again. So did you pick different number? Multiply that number by 4. Add 2 to that. Divide the sum by 2. Then subtract 1 from that. And write that down. So you have another original number and the result. So far you have 2 pairs, right? Let's have one more time. Pick the third different number. You got it? And multiply that by 4. Add 2 to the product. Divide the sum by 2. And subtract 1 from the quotient. Write down the result. Okay, let me pick anybody from my list here. How about Hayden? Where's Hayden? Hayden, what's your original number? Hold on, let me write that down. Okay, tell me your number, Hayden.
7.
7, that's original number, and your result was
14.
14. How about second number?
9.
9, and the
18.
result was 18. Third number,
I will pass.
you have it. Okay, let's give me another person. How about Mackenzie? 5, you got 5, and your resulting number? 10. Your second number? 2. 4. Third number? 3. 6. What pattern do you see? Is this similar to yours? Everybody? What pattern do you see? Oh, the result is double of the original number. So can we just conclude any number that I'm picking, the result should be double of that? Can you prove that? We may, but for now we have only specific cases, right? So we can assume, or we can put hypothesis there saying that the result number should be double of my original number, right? So this kind of reasoning, what do we call that? Inductive reasoning. Very nice. Reasoning. Where's my handwriting and the spelling? Okay. So later, when we are doing deductive reasoning, we're going to prove that, okay? All right. Using Zoom and the presentation at the same time is kind of a hassle for me. Okay, now in inductive reasoning, very important thing is counterexample. Because, well, we're gonna go from specific cases. There are so many specific cases. If you prove that result hypothesis you have, you cannot show every case there, right? So proving true show counterexample. That doesn't make that statement you made is true. Okay, so counterexample is very, very powerful. That is a specific case that makes the statement not true. Okay, then you can say, oh, this is false. Okay, you can conclude it. So how do you pick a counterexample? Let's look at this specific example here. Which of the following numbers is a counterexample to the following claim? I have a claim here. If P is a prime number, an odd prime number, then P plus 2 is also a prime number. Hey, what is a prime number?
It only goes into it, so
So you mean
like
the
5 times
factors,
more.
right? Yeah, thank you so much. So you have only two factors. One in itself, then it is a prime number. For example, 5. 5 has only 5 times 1. There's no other whole numbers that makes as a product of 5, right? 5 is just 1 times 5. What else? Any other example of a prime number?
7.
7. You can only make 7 by multiplying 1 and 7, 1 in itself. How about 9? Is it a prime number? No, why not? You just gave me the counter example. Thank you so much. Right? 9 is not a prime number, even if it's an odd number. So not all odd numbers are prime numbers, right? Because 3 times 3 also makes 9. So you have 1, 3, and 9 as factors. You have 3 of them, right? So it's not a prime number. So we know what prime numbers are. We also know what odd and even means, right? What's even? That could be the definition of an even number. We all know that 2, 4, 6, 8, those are even numbers, and 1, 3, 5, 7, those are odd numbers. So what's the definition of even numbers? Have you ever thought about that? The even numbers, 2, 4, 6, 8, da, 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 da. What do you see? If you use actual object, yes, please.
You can multiply them by 2.
Oh, you can divide them by 2 and there's no remainder. So it's divisible by 2, right? Why? Because even numbers, they always get paired up, right? So it is divisible by 2. Excellent. How about the odd numbers? If you divide it by 2, what do you get? There's a remainder 1. For 1, there's no remainder. So it can be written as this. Okay, so even number definition, the whole number even number is 2 times n when n is a whole number. Okay, you're gonna learn this notation. So this shows this is an element of the set. Okay, this is between element and the set. So n is element of a whole number. So I'm talking about just a whole number. Okay, whole number times 2 is always even whole number. Odd number is then either 2n plus 1 or 2n minus 1. Okay, for whole numbers, I will go with 2n minus 1 because we want to start from 1. Okay, so even and odd numbers, you don't have to know this now, but we're going to use it later. Okay, so let's go back to our assumption here. If P is an odd prime, it's like 3, 5, 7, 11, 13, 15, 17, 19. Those are odd prime numbers, right? Okay. If P is an odd prime, then P plus 2 is also a prime. Do you think it's true or false? Why? 3 plus 2?
7 plus
7 plus 2 is not a prime? Yeah, you just found the perfect counterexample. So let's think about this together. So we said P is an odd prime. And we're gonna see if P plus 2 is also an odd prime, also prime. is always prime? That's our question, right? And we have some numbers like 3, 5, 7, 9, 11, and so on and so on. We're gonna see if we plug in 3, is it an odd number prime? Yeah, 3 is an odd number prime, so we can check that. So 3 plus 2 is what? 5. That is a prime, right? So it's not a counterexample. How about 5? 5 is an odd prime number, so it's a good candidate. How about 5 plus 2? Is it a prime? So it is good. It doesn't give us, false statement there. So no, 7 is an odd prime. Yes, it's a good candidate. Let's see, 7 plus 2. It's 9. Is it a prime? 9 is not. We just talked about it, right? Because there's 3 as a factor as well. So 1, 3, 9. There are 3 factors. It's not only 2. So it's not true. Even if the statement, if statement was true, it is odd prime, but the result, conclusion was wrong. So it is a counterexample. Right? How about 9? Is it an odd prime number? No, it's not even a good candidate. You don't even have to take a look at that as a counterexample. Okay? How about 11? Is it an odd prime number? Yeah, so it's a good candidate. So 11 plus 2. What is it? Is it a prime? Yes. So all of this makes statement true. If you're using only these numbers, it's gonna give you true statements. You're gonna say, oh, that's true. I mean, you can conclude if P is an odd prime, then P plus 2 is also prime is true. But not really, because you can show one example that makes that statement false. That's called counterexample. When I was doing that, I said, oh, it's a good candidate, it's not a good candidate, and so on, right? So whenever you are doing the counterexample, you need to find the example that if the statement is true, but conclusion part, then statement is false. That is a counterexample, okay? And I think you will have a lot of examples in the homework problem, so I will just skip that part. Is it okay? All right. So let's move on to deductive reasoning. So inductive reasoning, we started from specific cases and went to the general conclusion, right? Deductive reasoning is the opposite way. So you are given the conclusion and you're gonna prove it is true. Okay? That is deductive reasoning. So deductive reasoning is the process of reasoning to a specific conclusion from a general statement, just like geometry theorems. Okay? Okay, so we are back to picking the number in the we did earlier. Okay? So when we had specific cases with specific numbers that you picked, it's called inductive reasoning. Now let's prove that deductively. So I'm gonna go back to that problem. Where was it? Here. Okay, so this was what we have. Let's see. Pick any number. So instead of picking a specific number like 2, 3, 4, we're gonna go generally. So for that, I can use any number n. How about that? We call it variable, right? Okay. So any number is n, and multiply the number by 4. So it's gonna be n times 4, or 4 times n. Or surely I can say 4n, right? So n times 4 is the same as 4 times n. You can use commutative property of multiplication, that's same as 4n. So I'm gonna simply just write 4n and add 2 to the product. So let's look at the terminology quickly. That's almost to cover. I'm gonna actually start from the addition. When you're adding two numbers like a plus b, let's say that's c. This is called sum, right? Sum of two numbers or sum of three numbers means you're adding all the numbers together and the answer is the sum, right? How about subtraction? What's the answer? What do we call that? The difference. If we multiply two things together, the answer is the product. If I divide something by another, like a divided by b, what do I call that answer? The quotient. Right? So we know the notation. Okay, now we had 4, multiply the number by 4 and add 2 to the product. This is product, right? Because we did multiplication. We're going to add 2 to that. So we can add 2 to this product, right? Then what do we do? Divide the sum. Now it's addition. Look at the big picture, okay? This is addition. So this is the sum of 4n and 2. Divide that by 2. Right? And then subtract 1 from this quotient. So subtract 1 from it. Are we good so far? Now, can we simplify this? Yes, we can, right? You see this big fraction can be we can break this into two parts, like 4n over 2 plus 2 over 2. Can I do that? Minus 1. So these two are exactly the same, right? And can we simplify this? 4n over 2? Yes. How? Divide by 2 for both numerator and denominator, right? So, what is it? It's 2 divided by 2, you get 1. So 2n over 1 is same as 2n. 2 over 2, 1. Minus 1. What do we have? 2n. Because n minus n, 1 minus 1 is 0. 0 plus something is itself, identity property. Right? So we can start from n and ends at 2n. What was our hypothesis there? Our result was always double of the first number, right? And we can prove it by using general number instead of specific numbers. So this is called deductive reasoning. Good? So yeah, we could prove the same thing deductively and inductively. Okay? So that's what we did. All right. Let me share my. Okay. So we got that. And we got the counter inductive. Okay. So we're basically done. So we just proved using deductive reasoning how that problem went. So this diagram just shows difference between inductive reasoning and deductive reasoning. If you go from specific number to general conclusion, it's going to be inductive reasoning. If you start from general number, or I mean not number, general idea to the specific cases, it will be deductive reasoning. So we now know the difference between those two. Okay? Okay, and I got these problems from your homework problem because we have some, actually we have a lot of time. Let's try this. Do you think this is inductive reasoning or deductive reasoning, first of all? How many of you think it's inductive reasoning? You can just raise your hand here, so your friend will see you. Inductive reasoning. Deductive reasoning. Okay, so those who think this is inductive reasoning, say why. Let's debate. I love debating. Why?
Because you're assuming,
Because you're assuming by looking at,
like, when you go to solve it, you're gonna assume, like, you're gonna make a guess about what it would be instead of going through the process and counting to 133.
Okay, that's a really good reason. Is there anybody who wants to support her idea? There's a lot of nodding. Please support her. If you think the same way. Or restate. Anybody? Come on. You need to show your support. Come on.
No, I'll agree with there. You don't want to count all the way to 103, so you're automatically gonna assume it's gonna be an A or another E.
So you're not gonna show every case there, right? But there are only some cases based upon the observation of specific cases here. We're gonna make a conclusion for the 100 or 103rd. So it is inductive reasoning. Good job, whoever said inductive reasoning. Big praise for that. Whoever thought deductive reasoning, do you have any reason why you thought deductive reasoning? Was that just a mistake? Okay, then it's fine. If you wanna argue and have a debate, I love it. Please, come on. Okay. All right. So we know this is inductive reasoning. Then how can we find 103rd letter in this sequence? Does anybody have any idea? Let's think about it. Let me put it here. Keep thinking, guys.
Well, there's 6 letters and there's 5 E's, so I feel like you would just count the amount of those till you get to 103, like in this section.
Okay. What's your name?
Maddie?
Maddie. Maddie just said there are 6 letters, but actually there are 2 letters.
2 letters, but 6, yeah.
6 terms that are repeating, that's what she meant. We know, right? So what she meant is this is repeating. So A, E, 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 E comes next, and then A, E, 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 E comes next. Next, and so on and so on. This is the same pattern. Okay, then what? Rachel? Say that again.
No, like
I have really bad hearing, and I don't have a hearing aid yet, so please say aloud.
come up with like an equation.
What kind of equation?
Probability.
What probability? I don't think probability was in here.
Find how many times that pattern can go into 100.
So how many? How? So let's look at A's first. How about that? A is on the first. I'm looking at A is on the first and 7 and 8, 9, 10, 11, 12, 13. You look at the pattern here, right? Then what? Which term has A after 13? How did you find that? At 5 or 6? So it's gonna be 19th term will be A, and 25th term will be A, and so on and so on. And the rest of it, it's all E's. Okay, from there, we proceeded along, right? Okay, good process of thinking. Then what? How about 103rd term? How can we find that? First term is A, 7th term is 13, 19th term is A, 25th term is A. You wanna go all the way near to 103rd? You can do that if you want to. That's one way, but it will take some time. Any other efficient way that you can think of?
Just do
You wanna divide it by?
6.
So let's look at these numbers. So we want to divide these numbers by 6 because every 6th term is A, right? If you divide this number by 6, what do you get? The remainder, whatever the quotient is, the remainder is 1. 1 divided by 6, nothing in the quotient, but there's 1 remainder. So I'm looking at only the remainder of 1 here. If I divide 7 by 6, what's the remainder? still 1. 7 divided by 6, quotient is 1. 6 times 1 is 6. There's 1 remainder, right? There's 1 remainder. How about this one? 6 times 2 is 12, plus 1 is 13, the remainder 1. 19. Divided by 6. 6 times 3 is 18. So there's one left, right? The remainder is 1. So all A comes up in these terms, and these terms always have remainder 1 when you divide that number by 6. So now what can we do? Exactly. So divide it by 6. If the remainder is 1, it will have A. Otherwise, it will be B. So divide it by 6. No division. 6 divided, 1 cannot be divided by 6. This is small. Okay, so 1 then 6 times 1 is 6. Subtract 43, 6 times 7, 42. What's the remainder? 1. So we know that 103rd term should be A. Yeah, we found it. Right? Okay, very good. So that's how you can find the 103rd term. So if you have similar problem in your homework, you should be able to solve it, right? I didn't hear any yes. Yeah? Okay. Let's try this one. You're gonna use inductive reasoning to predict the next 3 numbers in the pattern. Inductive reasoning, we are looking at this specific numbers by observing what's going on here, right? So, where are the numbers in this sequence? Okay. I'm pretty sure some of you already have found the pattern there. What do you see? Anybody?
Or multiplied by -2.
So you multiply previous number by -2. So let's see. I'm gonna multiply 3 by -2 until you get -6. Okay. How about 6 times -2? Is that positive 12? Yeah. Yes. Negative times negative is positive, right? So 6 times 2 is 12. Yes. How about 12 times -2? Do you get -24? Yes, very good. So we know that this will be, this will have the pattern of multiplying -2 to the previous number. So we know next 3 numbers in this pattern, right? So what comes next? So multiply this by -2, and you get 48. You multiply that by -2. What is it? 96? -2.
Oh.
96 and -2. It's gonna be positive, right? The double of 96. 192. Excellent. And we know next. Da, 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 da. Okay. We can also find general term for that, but this is not asking, and we want to spend not maybe we want to. This is a little bit complicated. Later, when you go to Math 235, you're gonna learn about arithmetic sequence and geometric sequence. Geometric sequence. So arithmetic sequence is when you add same number constantly. So just like previous example, like you have let's say just like 2, 6, and keep adding 4 to that. Keep adding 4 to that. 10, 14, 18, 22, and so on and so on. I keep adding the same number, the previous term. It's called arithmetic sequence. Geometric sequence is when you are multiplying same number constantly to the previous term. So for example, I'm going to multiply this time 4, like this example. So 8 and multiply that by 4 and you get, what is it? 32. Multiply that by 4, you get 28, and so on and so on. Right? That is called the geometric sequence. So arithmetic sequence, you can find the rule for that. In geometric sequence, you can also find the rule too. Today, we're gonna just go one of these. Which one do you wanna find out? Arithmetic sequence or geometric sequence? Whichever will help your homework. So tell me. Which one do you wanna do? Shall we do arithmetic then? Okay. So let's look at any pattern of geometric, arithmetic. You just get a 2, 6, 10, 14, right? So how can we find the nth term? So this is the first term, and this is the second term, and this is the third term, and that's the fourth term, and so on and so on. Let's suppose we're gonna find the 100th term. If you keep writing 100 numbers, it's gonna be it takes forever, and I don't want to do that. I don't want to waste my time like that. I want to be more efficiently finding the number. Okay, so what I'm going to do here is, let's compare these numbers that are changing. First, second, so I'm going to put that as nth term. So if I write 1, that means the first term, 2, second term, 3, third term, all the way to the nth term. Okay, and then I'm gonna put what's happening here. Okay, so first term is 2, second term is 6, and compared to the first one, I know that I added that by 4, right? And the third number, I added 4 to the second number, so I can rewrite this as second number plus 4, right? Let's look at the fourth number. Fourth number, I'm gonna add 4 to the third number. So this is the third number, right? And I'm just adding 4 to that. And so on and so on, we're gonna go. So if I rewrite this, this is the same as 2 plus. That 2 plus is not changing. Do you see that? What is changing is how many 4s are added. So I'm gonna have some relationship with 4 here too. So I just have 2 here, so can I just multiply this by 0? 4 times 0 is what? 0. 0 plus 2 is 2. So it is still equal. So I can do this, right? How about this one? 2 plus 4. 4 is 4 times 1. And this one, the third term, 2 plus 4 times what? How many 4s are there? 2. So it's 4 times 2. Oh, do you see the pattern now? Yeah. How about this one? 4 times 3. Compare that number that is changing because these numbers are fixed. 2, 2, 2, 2, plus, 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 4, 4, 4. These are fixed. It's not changing. So we know that nth term will have 2 plus 4 times something, right? So let's look at the number that is changing. Like this, 0, 1, 2, 3. These are changing according to the number of terms. 1, 2, 3, 4. These are changing too. Now let's look at the relationship between this number and that. 1 and 0, 2 and 1, 3 and 2, 4 and 3. You see that? These numbers in the result, the changing numbers are always 1 less than the number of terms, right? So what conclusion can we make here for nth term? We know that we're going to keep the same number here, 2 plus 4 times, right? It's not going to change, but what's changing? That is changing. That's always 1 less than the number of term. So what comes here? N minus 1. N minus 1, that's one less. That is the generalized term you can have for arithmetic sequence. Okay? And what is that for then? That is how much we keep adding. We keep adding 4 here. And that number goes here. And what is this number? That's the first number, isn't it? So we can generalize arithmetic term like this. For any first term a sub n1, a sub 1 means that's first term in the arithmetic sequence. The second number should be a sub 2, a sub 3, right? So a sub 2 is first number plus changing number. You keep adding d much. It gets already confusing, but actually not, because we are keep adding d to the previous term. So a sub 3 is then a sub 2 plus d, or that's the same as a sub 1 plus d plus d. Then our conclusion can be a sub n in the arithmetic sequence is always first number plus changing number, the d that we are adding, keep adding, times 1 less than the term. So that is the rule for arithmetic sequence. We can do the similar thing for geometric sequence too. Okay, so you don't have to do the whole thing here. Okay. All right, so now let's go back to our example here. Okay, now let's look at the counter example again. Right there, counter example. Find the counter example to show that the statement is incorrect. This is from your homework example too. Okay. So you're gonna find the counter example that the statement is false. The difference of any two counting numbers will be a counting number. Well, previously when we were doing the counting example, we had if then statement, remember? And you need to find the counter example as if statement true, but then statement false. This one, I don't have any if and then, right? So you can find it. What's the condition here? The difference of any two counting numbers. So you're gonna have difference of any two counting numbers there. And you're gonna find that result is not a counting number. Then that's a good counting example. Okay? So we're gonna look at the difference. All of these show differences. So yes, they are all good candidates, right? So let's see if the statement, if that gives you the wrong answer, then it is a good counting example. So 10 minus 2 is 8. Is 8 counting number? 1, 2, 3, 4, 5, 6, 7, 8. 8 is a counting number, right? It's called a natural number, fancy name. So yeah, it is a counting number. So that doesn't give the counter example, right? Because it makes it true. So we're gonna find the counter example that makes this statement false. So no, not this one. How about this? 3 minus 5. It is a difference of any two counting numbers, because 3 is counting numbers, 5 is a counting number, 3 minus 5 is difference between two counting numbers. Now let's look at this number. Negative 2. Is negative 2 a counting number? No, it's not. Counting number starts from 1. 1, 2, 3, 4, 5, Those are counting numbers. Negative 2 is not a counting number. It's a negative integer. So yeah. So this statement here, 3 minus 5, is the difference between any two counting numbers. But the answer is not a counting number. So it is a good counting example. Does it make sense? Okay, how about this one? 7 minus 4. Difference of any two counting numbers. Yes, right? So good candidate. How about the answer? 3. Is it a counting number or not? It is a counting number. So it doesn't give us wrong answer. So it doesn't give us the counting example. Make sense? So the answer should be B. Any question for that? Okay, good. This is also from the we're almost done. Let me give you one last counter example because counter example to some people is really hard. Okay, let's find the counter example to show this statement is incorrect. When a counting number is added to 3 and the sum is divided by 2, the quotient will be an even number. So meeting all these conditions up until comma, but it's not an even number, then it's a good counting example, right? Keeping that in mind, let's look at this. When a counting number is added by 3, so a counting number 2 is added by 3, yes, right? And then the sum is divided by 2, so yes, this is a good, good candidate, right? And the answer is 5 over 2. Is that an even number? No, it's not. So yes, it's a good counting example, isn't it? Yes. How about this one? 8 plus 4. It's not even a good candidate, right? Because it doesn't have any counting number added by 3. It's added by 4 or added by 8. So not even a good candidate. You see that? You just cross it out. How about this one? How about this one? 10 over 2, is that a counting number? Think about it. It looks like fraction, but 10 over 2 is 5. 5 is counting number, right? So it is a good candidate too, because the counting number is added by 3. Yeah, right? So, and the sum divided by 2, hey, the sum is not divided by 2. So actually this is not right, because it didn't actually divide the whole thing by 2, but instead it is divided in one part of it. It's not even a good candidate either. You don't even have to look at the answer. Okay? So the answer should be A. Any question for counting example? All right. Okay, that's it. And your first homework is due Friday. Okay, before our class at 11. And if I miss anybody for the attendance today,